In this section of chapter 3, we are going to learn about mass percents and learn how to calculate the empirical formula for any substance. So what are we talking about here, okay, with the empirical formulas and whatnot? So for example, when you look at any compound, it has a certain ratio, okay? So when you say, okay, we have nitrogen and oxygen forming a compound, it has a particular ratio, 1:1 or 1:3. And how do we find those out? Okay, that's kind of what our purpose is in this chapter. So we'll go forward and backwards, and try to figure out the percent values and also empirical formulas, which is how do we know what the ratio is, okay, for different elements. So before we get into that, let's talk a little bit about chemical formulas themselves. All right, so there are three different kinds of formulas. The first one is empirical formula, which is considered to be the lowest ratio that's possible for any kind of a compound, the lowest ratio possible. Okay, so water, for example, H2O and then CH2O. Molecular formula is the actual ratio. For a lot of compounds, the empirical formula is also the molecular formula, like water, H2O. H2O is still H2O, okay? It's not H4O2 or it's not any other combination. That's what it is. So empirical formula is sometimes the molecular formula also, but in some cases it's not, okay? So for example, in the case of CH2O, in an empirical formula, if you multiply that by 6, then you get the formula for glucose, which is C6H12O6. So you multiplied each of these numbers, the ratios, by 6. So two questions. Number one, what is this? And number two, how do we get 6? So this glucose, how did we get glucose, first of all? Okay, so glucose is something that occurs, all right? So an empirical formula can also occur, but molecular formulas also exist, okay, in nature, or we make them in lab. The number 6 comes from experimental determination, okay? So there is no other way for us to know that you have to multiply this formula by 6, okay? So we'll talk about it later if we get a chance, but otherwise know that this number actually comes from instrumentation, from doing experiments in the lab, okay? Otherwise there is no way for us to know that you need to multiply it by 6. Now, one last thing I want to mention about empirical formulas and molecular formulas is, like, why do we have them? Okay, so for example, we are multiplying by 6. Can we multiply by 4? You can. Does that compound exist or not? That's a different thing. But you can take CH2O and multiply it by 3 and 4 and 5 and get a molecular formula. Now, whether those compounds exist or not, that is something to be determined in the lab. All right, so it's not that you can just multiply randomly also, okay? So this is something that, you always have to verify. The final structure, the final formula, I should say, is the structural formula, and this is a 3D representation, which we will do a lot later. In this portion, in this section, we're going to focus on empirical formulas and molecular formulas, and of course mass percents, okay, which is where we're going to start. So a mass percent of anything is, of course, just the percentage of anything. Percent means out of 100, right? So if you're trying to find the mass percent of an element in a compound, you will take that mass of the element over the total mass, okay? So if you're trying to find out the mass percent of your head compared to your whole body, you need to have the mass of your head and then the mass of the whole body. You divide the two times 100% and you get the mass percent, okay, of your head. So that's kind of what we're doing here, except we're doing it with compounds, okay? That's all it is. So I need to remind you of something that I spoke about before, and that is when you look at a formula, I would like you to look at that formula in terms of moles, okay, and mole ratio. So here, for example, in sodium carbonate, there are 2 sodiums, 1 carbon, and 3 oxygen. But I want you to change your thinking just very slightly and not think of this as just 2 sodium, think of it as 2 moles of sodium, okay? 1 mole of carbon, 3 moles of oxygen. And that kind of thinking is going to really help you in chemistry with the calculations and all, okay? So again, 2 moles of sodium, 1 mole of carbon, and then 3 moles of oxygen. Okay, so look at compounds in terms of mole ratios. Okay, so here is where calculation for mass percent. So silver chromate, which is given, the formula is given here, is used in the lab for staining, and what is the percent of each element in silver chromate. So to find that out, you first need to find the total mass of silver chromate, which we have already done before, so no need to go over it. Just make sure that all the masses are correct, and then everything should be fine. You know how to calculate molecular weights. So you get the final weight, okay, over here. Now, do you want to leave it to 3 decimal places or 2 decimal places? I will leave that to you. Over here, I just went ahead and carried on the 3 decimal places, because remember we talked about that you can have up to 2 decimal places, and that's sufficient, and usually that will be sufficient. So now to convert each component to the mass percent, make sure to take the entire mass, okay, of oxygen and chromium and silver, not just one. So because you have 2 silvers, you don't have 1 silver. So make sure you take 215 over the total mass, not 107.9. Okay, so you need to make sure you take the total mass of silver over the total mass of the compound times 100%. Okay, now the grams per mole that we have here, even if you were working with AMU, it is not going to matter, because you're going to cross those units out eventually. All right, so I wrote the units out, but you don't really have to. So I mean, I'm just not encouraging you to not write units. I'm just saying that they will get crossed out. So even if you're working in AMU, it's totally fine. Okay, so you do that for each element. So you take silver, then chromium is only 1, so 51.99 divided by the total weight times 100%. And here I've rounded everything off to 2 decimal places. Okay, so we have some consistency here, and so then you have your final answers. Now, the last thing you should do, and you don't have to do this all the time, is initially you may want to do it, is make sure that everything adds up to 100, because since everything is out of a percent, cent means 100. Okay, so everything should add up to 100 at the end. So that's a good cross check to do. You don't have to add the decimal points. Just do a quick check, with just the whole numbers, and you will see you are okay. If you're okay, you're good. If not, then go back and see what you missed out. Okay. All right, so here is another one. Gram of an element in gram of a compound. Okay, so a little bit different here. The chemical name of table sugar is sucrose. So C12H22O11, and yes, thank God for sugars, because can't live without them. How many grams of oxygen are in 68.1 gram of sucrose? So first we find the molar mass. Everything we have to find the molar mass. So here's the molar mass of sucrose. So it's 342.96. Okay, grams per mole of sucrose. Now to find the mass of carbon, just carbon, or is it oxygen? I'm sorry, this should be oxygen here. So to find the mass of oxygen in here, so you need to find how many oxygens you had, and you had 176 grams of oxygen in 342 grams of sucrose. That's your ratio, okay, that you have, and that ratio is like a conversion factor for you, and that conversion factor you are going to use here for 68.1 grams. So you're asked how many grams of oxygen you have in sucrose. So 68.1 grams of sucrose will have, then you use your conversion factor, because now in 342.30, so I rounded it off here to say to 2 decimal places, you have 176 grams. Okay, so this is your conversion factor, and that will give you then your grams of oxygen, okay, in there. So yeah, I will change that in a bit. Actually, I could do that right now, so that way we will have at least correct one here. Okay, all right, sorry about that. So now let's go on to next problem. Percent water in hydrate. So in the percent water of hydrate, what is the percent of water in copper 2 sulfate pentahydrate? So here is the formula. Now sometimes I don't give you the formulas, okay? So you should be good with your nomenclature. So copper 2 sulfate is right here. So where you have 1 copper, 1 sulfur, 4 oxygen. So you add up the weights. You find the weight of 5 water. So 2 hydrogen, 1 oxygen, that give you 18. 18 times 5, because we have 5 molecules of water, that is 91. Add everything up. That is the total mass, okay, of the pentahydrate. Now to find just the amount of water, you just need to take the water mass divided by the total times 100%. So there is about 36% of water in this. Not very hard, right? Okay, now we're going to go backward, okay, which means that we're going to find empirical formulas. So what we did just now was found the mass percents. Now we're going to calculate empirical formulas, which is actually the formula, okay, for anything. So again, remember there are two things. There is an empirical formula and then there is a molecular formula. The empirical formula is the lowest ratio and the molecular formula is the actual ratio. Now, here I've given you an example of N2O4 and NO2, okay? So NO2 is the empirical formula and N2O4 is the molecular formula, is the actual ratio that you might have. Strangely here, both of these can exist, okay? So that's not an issue and that's not something that I'm going to ask you whether something exists or not. But the thing is, you should know that N2O4 is a molecular formula because you can divide this by 2 in order to get an empirical formula. Okay, so I hope you understand what I'm trying to say. Empirical formula is the lowest ratio, okay, that you have to do. Okay, so to find empirical formulas for anything, you need to know the mass percents, okay, of some of these things. So that's what we're going to have to do. Now, one last thing I want to mention here before I go on. When we have empirical formulas, okay, given to us, and we are not told that you need to multiply by 2, okay, you need to find the molecular mass, but you're only given, the molecular formula, but you're only given the empirical formula, okay? So to go from empirical formula to the molecular formula, you need to multiply it by an integer. How do you find that integer? So I talked to you about that, a little bit before earlier on with the glucose. So that integer you have to find by finding the mass of the molecular formula. Okay, so if you know the mass of N2O4, then you know that this empirical formula has to be multiplied by 2 in order to get that molecular formula. So I'm going to explain that to you as we go on also, okay? So if that's confusing for you right now, don't worry about that, okay? But that integer we find usually by what an instrument called mass spectrophotometer, okay, in the lab. So that actually finds the mass of any substance. Empirical formula itself is not determined by the mass spectrophotometer. For determining the empirical formula, you do something which is called an elemental analysis. Elemental analysis is when you take your sample and you burn the heck out of it, so which means you burn it in oxygen. So everything that you are burning in there, any element, will then be combined with oxygen. So if you have hydrogen, it will combine with oxygen to give water. If you have carbon, it will combine with oxygen to give carbon dioxide, so on and so forth. And then you have all these different components in there which will absorb all these different gases, and then you have to do back calculations. So it's a lot of calculations that you have to do in order to figure out the empirical formula. Okay, so we are going to start with the mass percents. We're not going to start with carbon dioxides. Okay, so don't worry about that. So I'm cutting it down a little bit for you, okay, in here. So to determine the empirical formula, you will be given mass percents. Okay, so we did mass percent already. Now we're going backward. All right. So when you're given mass percent of something, it means you can presume that you're dealing with 100 grams of a substance. So if you have 39% carbon, it means that you have 39 grams of carbon in 100 grams of the substance, okay, in there. So that's how you're going to presume. Then this is the stepwise way of getting there. So you convert grams to moles, and then once you have the grams to moles, then you're going to do the mole ratio. Okay, so remember I've said to you that everything you have to do in mole ratio, right? So you have to find the mole ratio of something. Now, right now, all of this is not going to make any sense to you, so I'm going to talk about this later on, but it's given over here, so you can always come back and check, because once you divide these numbers, you don't get whole numbers all the time. Okay, so you're going to get decimal points, and so when you get fractions or decimal points, you have to know how to round off. Okay, so I'm going to explain this to you as we do the calculations, but later on when you need to check for yourself, you can always come back here and check. Okay, so how to do it if the decimal point is really close to rounding off to 1 or 2, but if it is 0.5, then you have to multiply with different numbers, okay, in order to get a whole number. Because remember, when you have an empirical formula or a molecular formula, that formula is never going to be in decimal points. And what I mean by that, okay, is that if you have carbon dioxide, it's a 1 to 2 ratio. Okay, it's not 1 to 1.5 ratio. That's not possible. That was Dalton's atomic theory, that any kind of an element will combine in whole numbers. So if you're getting a mole ratio of 1.5 or 1.5, then what do? So then you have to multiply it by 2, you'll get 3. So which means then your ratio is 2 to 3, which is still the lowest ratio, right? Because you have to multiply everything by 2 in order to get that. So that's kind of what I'm saying. Okay, you cannot have decimal points as your mole ratio. All right, so we'll do that also as we go on. Okay, so once you have the empirical formula, then you have to determine the molecular formula. In order to determine the molecular formula, you need to know the molecular mass. If you don't know the molecular mass, then you need to know the integer, right, with which to multiply the empirical formula with. So either thing you need to know. Either you need to know the integer or you need to know the molecular mass. So I have to give you either of those in order for you to figure out the molecular mass, okay, or the molecular formula. Otherwise, it's not going to work out. Okay, so let's look over here for a very simple calculation. This is just so that you can understand the difference between molecular formula and an empirical formula, okay? So here's a compound with an empirical formula of CH, okay? So you've done all the calculations and everything. So the empirical formula is CH. So then I have to give you the molecular mass, right? That's what I said. So the molecular mass was found to be 58.02 grams per mole. What is the molecular formula? The molecular mass was found to be 58.02. How did we find this mass? This is what I was saying, that you use the mass spectrophotometer in order to find this mass. It's an instrument, okay, that we use. So it's not something that we're just pulling out of our head, okay? So you have to use instrumentation to figure this number out. Okay, so then what's the molecular formula? So the empirical formula is CH. So what you do is you find the weight of CH. So CH is 1 carbon, 1 hydrogen. So 1 carbon, 1 hydrogen is equal to 13.018. This is the mass of the empirical formula. So now what you do is you take your molecular formula mass, which is 58.08, divided by the empirical formula weight. So 52.08 divided by 13 will give you 4. So which means the integer that you need to multiply with is actually 4. So which means the molecular formula is C4H4. Okay, so see how that works. Once you have your empirical formula, you find the mass of that, and then you divide the molecular weight with that mass. And that will give you your integer that you need to multiply with. Okay, so we'll do some calculations with that too, but this is just to kind of get you warmed up. Okay, so calculating empirical formula, sodium whatever pyrophosphate, okay, is used in detergent preparations. It's composed of 34.5% of sodium, then there is phosphorus, and then there's oxygen. So again, let me remind you, a long time ago I was talking about oxygen and how do you know that you're dealing with oxygen as an O or oxygen as an O2, because you know that's an issue right there. That's how we deal with it. Okay, so here it is given to you as O and not O2. So keep in mind, okay, be very clear in how you do your calculations. Every calculation we've done so far has been with O as in atoms. Okay, we're not dealing with O as in O2 as a molecule. All right, so make sure you keep those things separate. Okay. Okay, so those are the percents given to us. So what is the empirical formula? So the first step to do is convert all the percents to grams and then find the moles. Okay, and what does that mean? It means if you have 34.5% of sodium, it means it's 34.5 grams of sodium, because you're going to assume that the total mass of the compound is 100%, okay, or which is then 100 grams. So in 100 grams, you have 34.5 grams of sodium, 23.3 grams of phosphorus, and 42.1 gram of oxygen, okay? So now you convert everything into moles. What are we trying to do here? We're trying to find the mole ratio. Okay, eventually, so eventually we'll find the mole ratio. Right now we're just trying to find the moles. So we have moles of sodium and phosphorus and oxygen. Okay, so now if you write out the formula, your formula is going to look something like this, that sodium is 1.5 and phosphorus is 0.75 and then oxygen is 2.6, and it is totally not possible to have something like this, okay, because everything is in decimal points. So to eliminate that, the first thing that you do is you divide everything by the smallest moles, so which is 0.75. So you divide everything by 0.75, which is what I have done. I'm writing it here too, but I have done that here. Okay, so you take all of these moles and then you divide it by the smallest number and then see what kind of numbers you get. Okay, so it will bring it down to your lowest ratio. Remember, empirical formula is lowest ratio. So it turns out that we are very lucky. Of course we are lucky. We're always lucky, right? So here 1.5 divided by 0.75 will give us 2. If you get 1.99, you can round it off to 2. Don't leave it as any kind of a fraction, okay? So then here, this one of course should be 1 because, you know, we're just dividing it by the smallest number. And so then the other one come out to be 3.5, okay? So 3.5, now that should kind of wake you up. You're like, oh no, this is not good. So if this is coming out to be 3.5, then what you're going to do is you're going to take all of these and you're going to multiply them by 2. Okay, everything, not just one of them. Okay, everything you will multiply by 2. So which means that this becomes 4, this becomes 2, this becomes 7. Okay, and so then you end up getting your mass numbers. And then let me go ahead and erase this one. So right here, you multiply everything by 2 there. That is how you will get your final formula then. Okay, so again, you can see here that you cannot divide this any further. So this is the smallest ratio. And you cannot have decimal points, okay, which is why we had to take the 3.5 and multiply it by 2, okay, in order to get the 7. So that is kind of how you do these calculations, okay? So again, get the number of moles, divide it by the smallest number. Once you divide it by the smallest number, make sure you have whole numbers. If not, then get rid of that decimal point. If it is 3.3, you multiply it by 3, okay, because that's a third. Now, typically, you will not have a 3.25, so you should not have to multiply by 4. Usually, you have to multiply by 2 or 3, okay, in order to get a whole number. That should be sufficient, okay, because if you get 2.25, maybe something is wrong somewhere, okay, all right. So here's another example. So benzene is composed of 19.3% carbon and then hydrogen. What is the empirical formula of benzene? the molecular weight is given to us, and what we're asked to calculate the molecular formula also, okay, in this case. Okay, so we start the same way, which is 92.3 grams of carbon, convert that into moles. So, just doing the mole conversion here. So 1 mole has 12.01 grams of carbon. So find out the moles of carbon, find out the moles of hydrogen. Once you have that, here I've done the step 2 in a very shortcut kind of a way, and you can do that as well, because now what you have to do in the second step is to divide by the smaller number. Okay, the smaller number here is 7.64. So you divide both of these by 7.64 and you get 1 and 1. So no rounding off necessary here. So empirical formula is then CH. Okay, so one part done. Now we know that the molecular weight is 78.1. Now we have to find the molecular formula. Okay, so the empirical formula weight is 1 carbon and 1 hydrogen, which is 13 AMU. And now you take the molecular weight divided by the formula weight, and you get an integer of 6. So 78.1 divided by 13. Okay, 78 was given to us. 13 you found out because you found out the empirical formula. So then you found out the integer, which is 6, and that gives you C6H6, and that is the molecular formula for benzene. Okay, and the empirical formula was CH. So you can see that in order to go from empirical formula to molecular formula, you need to have the molecular mass, okay, which is given to you. So that's what you need in order to know what to multiply it with. Okay, here is another one. So same kind of thing. Okay, so again, you are given percents and you're given the molecular weight. You're asked to find the molecular formula. So again, I've done, really quickly over here everything. So this is, converting carbons to give you moles of carbon and then moles of hydrogen. Again, remember, you're just converting all the percents to grams. Okay, and so then you find the moles of everything. Once you have the moles, remember the second step is to divide by the smallest number. The smallest number is 1.7. So divide all of these moles by the smallest number in there, and the smallest number then is 1.7. Then you get 1 for hydrogen, and then oops, this should be nitrogen over here. Okay, I'll correct that. And then the other numbers here for carbon and hydrogen are the C3 and then 8, okay, over there. So let me correct that here. This is nitrogen. So then your empirical formula comes out to be C3H8N, okay. Now, if you're wondering how to write this, okay, by the way, like, can you write H8NC3? Can you write that? At this point, sure, you can write whatever you want, okay? But technically speaking, in chemistry, there is actually a sequential way of writing elements, okay? But at this time, I'm going to let that go. So you can write whichever one you want first. So that's totally fine. So long your mole ratios are correct, it's fine, okay? When you have compounds that you're trying to name, like ionic compounds, you write again whatever is on the left-hand side, you write first, okay? But this one, hydrogen, is always going to be on the left, so you can't write that first, okay? So carbon is on the left-hand side, so you write that first, and then you write hydrogen, then you write nitrogen. Okay, then step number 3. Step number 2 was just to find out the mole ratios and come up with the empirical formula. So here we were lucky, we didn't have any decimal points, okay? Otherwise we would have to multiply something, with 2 or 3, so we don't have to. So then the last step that we have here is to figure out the molecular formula. So we first have to find the mass of the empirical formula for C3H8N. So right here, that's the calculation given to you. So the total mass is 58.104 for empirical formula. So now you take the molecular weight that's given to you, 116, divided by the weight of the empirical formula, and you have the integer 2. So you take the empirical formula, multiply it by 2, and that's how you will get your final molecular formula, okay, in there. So yeah, you can ignore all of this. That's fine. Okay, all right. So hopefully you're getting more comfortable, okay, with how to calculate all of this, because that's all I have for you in this slides. Okay, all right.